Hello everyone, welcome back. In this video, we'll be discussing about the third problem of today's biweekly contest. Count the number of incremovable subarrays to. As always, we will start from the very brute force solution and understand the thought process behind each and every optimization. If you stick till the end, I'm very sure you will not only be able to solve this problem by yourself, but understand the thought process which you can apply in future problems as well. So with that, let's get started. The problem states that you are given a zero-indexed array of positive integers nums. A subarray is called incremovable if nums become strictly increasing on removing the subarray. For example, if you remove the subarray 3, 4 from this array, the resultant array would become 5, 6, 7, which is strictly increasing, and hence 3, 4 is a incremovable subarray. That is, by removal of this subarray, the array becomes strictly increasing. Our task is to find the total number of incremovable subarrays. So let's take an example. Let's say this is the array 8766. There are three incremovable subarrays here. First, 876. If you remove this subarray, the only array element remains is 6, which in itself is a increasing array. If you remove 766, only element remains is 8, which again is a increasing array in itself. The third thing that you can remove is 8766. You remove the entire elements from the array. An empty array is also strictly increasing, and hence there are three subarrays or three incremovable arrays which you can remove such that the resultant array would become strictly increasing, and hence the answer here is 3, right? So hope the problem statement is clear. Now how to solve this? So if you haven't thought about the brute force solution yet, I would strongly encourage you to pause and try to come up with the brute force solution by yourself. So hope you have thought about it. What will be the brute force solution? We need to remove a subarray such that the resultant array would become strictly increasing. For example, if you remove the subarray, the resultant array contains 6, 7, 8 and 9, and which is strictly increasing. So we need to remove subarrays. A subarray, the brute force solution could be try removing every possible subarray, see the resultant array and check whether it is strictly increasing or not. If it is strictly increasing, our job is done. We found a incremovable array. Otherwise, we will keep on trying with other subarrays. So what I'm trying to say here is, we will, let's say, pick two variables L and R, right? Because a subarray can be defined by L and R. So we will try all possible subarray. So we will start our L all the way from here, and we will start our R from here, here, here and here. So this L and R would mean we are removing this subarray, and after removal of this subarray, this is the array which is remaining. So we'll just check if this remaining array is strictly increasing or not. In this case it is, so we'll just increment 1 to our answer. Similarly, we will try other possible scenarios. Let's say let's say we take this R, so in this case, and this L. In this case what we are saying is we are removing this particular subarray. So if you remove this subarray, the resultant array would become 6, 7, 8, 8, 9, which is increasing but not strictly increasing, because at this position these two elements are equal. So we want the resulting array to be strictly increasing. So this is not a valid, this L R is not a valid incremovable array, so we'll not increment +1. So we'll keep on doing this for all the subarrays and check whether the resultant array is strictly increasing or not, right? So what is the pseudocode? The pseudocode would be very simple. It will look something like this. So what we will do, we'll try out all possible subarray. So we'll try out every L and R, right? Now for each subarray, what we want to do, we want to remove that particular subarray and then check whether the resultant thing is strictly increasing or not, right? So one way to check strictly increasing could be just start your journey from here, check whether everything up till L is strictly increasing or not. Okay, so this is what this part of the pseudo code is doing. We are checking everything up till L is good or not, right? Now after that we'll also check if everything after R is good or not, right? So this part of the pseudo code is doing exactly that, right? We are checking whether everything after R is strictly increasing or not. Now if this part is strictly increasing, this part is strictly increasing, we will simply check whether the value at L minus 1 and the value at R plus 1, whether L minus 1 value is smaller than the R plus 1 value. Only then this complete array would become strictly increasing, right? So that's what we are checking at the end. We check if everything up till L is strictly increasing, everything up till R is strictly increasing, and the value at L minus 1 and the value as N minus 1 is strictly less than the value at R plus 1. If all these criteria are satisfied, then the resultant array would be a strictly increasing array and the removed subarray would be a valid incremovable array, and we will simply do result plus plus, right? So we will keep on doing this for all L and R, and finally we'll get how many subarrays are there which are incremovable. Now what is the time complexity of this entire approach? So we are doing two loops here, so that's basically n square, straightforward. We are trying out every possible subarray, so n square subarrays and hence n square. Now for each subarray, what we are doing, we are checking everything in the left whether they are strictly increasing or not. So in worst case that can go all the way up to order n. Similarly we are also checking everything in the right after R is valid or not. Again in worst case that can go up to order n, right? In reality if you like this, if you sum them all up, that in worst case can be order n, but doesn't matter, like it just add a constant factor, and after that we are doing some operation which is kind of order 1 operations, right? So in total the complexity of this entire algorithm is order n cube, right? Which surely will not pass because n is 10 raised power 5. Even n square will not pass, right? But this is the very brute force solution. So if you haven't understand anything here, I would encourage you to rewind and at least understand this part before moving forward. Now we need to optimize this, right? Which of these, there are three n's, right? Two n's are coming from the fact that we are trying out every possible subarray, and one n is coming from the fact that we are checking whether everything in the left is good, whether everything in the right is good. Because of these two, the last n is coming, right? If so, if you have to remove this, optimize this n cube to let's say n square, you need to remove one of these n's, right? Even n square will not work, but we have to first take it to n square at least, otherwise then only we'll be able to optimize it further, right? So which of these three n's will you remove and how is the question. So if you are following this channel for a while, I would strongly encourage you to pause, and I'm sure you will be able to at least get some clue about which of these n's are easy to remove. So hope you thought about it at least. So this removing these two n's would mean that we are not trying out every subarray. and still we are somehow able to figure out how many equi-removable arrays are there. So removing one of these two n is very hard. We just think about it, if you don't try every subarray, how would you be able to answer, or how would you be able to determine which subarray is good or not? So removing these and these two n's is difficult than removing this n, right? So let's see if we can remove this n first, right? And the answer here is we will be able to remove this n very easily. How? Think about it. We have these two loops, what they are doing. Let's focus on this one first. If they're checking, this loop is checking whether everything up till L is strictly increasing. So if L is this, it will be checking whether everything up till L minus 1 is strictly increasing or not, right? Now let's say L becomes this, then also it will be checking whether everything up till this is strictly increasing or not, right? So whatever it has checked before, if we increase the L, it will also check all of these again along with just one new check. For this all things, it has already checked whether it is less than this, whether it is less than this, whether it is less than this, and so on and so forth. Now for when you increment L, you are adding one new check, which is whether this is less than this, right? That's the only thing you are doing. But because you don't save any computations from before, you have to iterate over the entire thing again, right? So hope you understand that there is something you can save here. So if you haven't got the solution previously, this is the right time to pause and try it yourself. So the catch here is, if we are interested in strictly increasing arrays, right? So let's say this part is strictly increasing. We know that, like we can just do a while, we can do a while loop and figure out up till which index we have strictly increasing values. After that, once this breaks, no matter which L you choose, everything will be for everything this good till L will be false, right? So what we can do is we can simply figure out the max good left index, and whenever we have to check whether everything before L is good or not, we'll simply check whether L lies within this max of L or it lies afterwards, and with just one comparison we'll be able to tell whether everything up till L is strictly increasing or not, right? So if we take an example, in this case, let's say you started a loop. Let's just get rid of all of this. Let's say you started a initial loop, and you just figure out up till which index everything is increasing. How will you do that? Let's say you start your loop from 0. You will check whether 1 is greater than 0. If it is, you increment your I. Again, when you are at 1, you will check whether 2 is greater than 1. If it is, you will increment your I. You will check whether 3 is greater than 2. The answer is no, because the value at 3 is 2 and the value at 2 is 8. So 3 is not greater than 2. So we'll stop here. It means this is what is strictly increasing. Everything after that is not will not come under strictly increasing section. So when you have to, let's say the value of L is this, so you can simply check whether this is less than equals to I plus 1. If it is, the answer is yes. So in this case the answer is yes, because you know everything up till I is strictly increasing, so everything up till 1 must be strictly increasing as well. Now if L is this, then you know everything up till I is strictly increasing, but what we need to check is whether everything up till 3 is strictly increasing, which is not the case. So you will simply return false here, right? So hope you understand how to remove this loop with just a single operation. And in the same fashion, you can remove this loop, this second loop as well. How? You can simply keep track of up till which index everything is strictly increasing on the right side. So this is the part which is strictly increasing on the right side. So you can simply maintain max R or min R, whatever you call it, and whenever you have to query for R, you will simply check whether it lies within this range or outside this range, right? Now again, how will you figure out this max of R or min of R? Simple. You will start from the last index. You will check whether the previous index is smaller. If it is, you will move your I. Whether the previous index is smaller, yes, move your I. Smaller, yes, move your I. Previous index is smaller, yes, move your I. Whether the previous index is smaller, the answer is no, because the value of the previous index is 8, current index value is 1, so 8 is not less than 1, so we'll stop here, and everything up till after this is strictly increasing, and hence everything, if any R which lies in this range will have a value of true, everything else will have a value of false, right? So we can simply remove this for loop as well with just order one operation, just single comparison. So we removed this, we replaced this with order one operation, we replaced this loop with order one operation, and this was order one itself. So overall complexity is now order n square, right? So the pseudocode will simply be modified like this. Previously we were iterating over everything to figure out whether everything up till L is good or not. Now we'll simply do a comparison operation max with max good and left. And how to find max good and left, we discussed that. We can simply figure it out before we are entering this loop. Somewhere before we will figure out max good and left and max good and right, and that will take just order n time. So overall complexity now is just order n square, but as discussed, order n square will also not pass. Now how will you optimize this? Again, optimization is just a matter of one small observation here, so pause it and try to think by yourself. So optimization here would mean that you have to now remove one of these loop, right? So we have n square algorithm here. First n is coming from this L, basically we are iterating over all possible L's. Second n is coming from this R, iterating over all possible R for a particular L. Now if we have to reduce this, we have to remove one of these loop, no choice, right? So let's try to remove, like removing any one of these is identical, right? So let's remove this R, or let's try to remove this R. So what this means, let's say you have a particular L, right? Now removing R, or removing iterating over all the possible values of R would mean that from this L you have to figure out what all good R's are there without even iterating over them in order 1 or order log n or root n kind of operations, right? So what look at this carefully, what we are doing inside this thing, right? So we are iterating over L, so we already know whether everything up till L is good or not, right? So if it is not good, we'll not consider that L at all, because if good till L is false, this entire thing will be false and we will not increment the result. So we will only iterate over the L which are good. So in other words, instead of going all the way till L, we will only go all the way till max good in left, right? So that is one thing which is obvious, pretty obvious. Now this condition goes away if we start from 0 and go all the way to max good in left, because this is implicit now that good till L will be true, so we can remove this. Now what is remaining? Remaining piece is we have to figure out a value which is greater than array of L minus 1, and everything after that R should be strictly increasing as well, right? So we already know that what up till what point everything in the right is strictly increasing. We know if R is anything after this, these this will fall under strictly increasing category. Basically this good till R will be true only for them. So we already know a possible range of R, right? But not all of these R's are valid. Only the R which satisfy this criteria will be valid. Just to reiterate, we already removed good till L condition, because now we are saying instead of going from all the way to 0 to n, we will just go from all the way to 0 to max of good and left. Now two conditions left. One, whatever R we choose, that should fall under strictly increasing range, and second, whatever R will choose, the array of L minus 1 should be less than the value of array of R plus 1. So to satisfy this condition, we already know the value of R should only be in this particular range, basically everything after max of good and right. So if we only consider R in this particular range, we can simply erase this condition as well, because we are taking care of it as well. Now after we know that R will be in this range, only thing we need to take care is array of L minus 1 should be less than array of R plus 1. In other words, in this particular example, array of L minus 1 is 6. So we need to figure out in this range a index where array of R plus 1 is greater than is greater than 6. So in this case it would be this particular R. So basically this is the index where array of R plus 1 is greater than the given value. So everything after this will be valid, right? So if you think logically, if you remove this array, 6, 7, 8, 9 is a valid strictly increasing array. Now if you remove this array, 6, 8, 9 will also be a valid increasing array. If you remove this array, 6, 9 is a valid strictly increasing array, and finally if you remove this thing, only 6 is also a valid increasing array. So what we want now is a way to figure out the starting point after which everything will be strictly after which everything will be forming a valid strictly increasing array. So if we know the value of the starting value of R, this is not the R, this is max of R, right? So if we know the starting value of R, we can simply do result plus equals n minus R plus 1, right? So this is, let's just make it result. So we can simply do this if we know the value, the starting value of R. And what is the starting value of R? The first index where array of L minus 1 is less than array of R plus 1. You can call it R as well if you just remove the indices. So we need to just figure out what is the first point where the value is greater than 6. Now notice this part of the array is already sorted because of the assumption that we are only considering everything which is strictly increasing. So this part of the array is already sorted, and we need to just find out the first point where the value is greater than 6, which we can do using binary search. Okay, so we can simply figure out this point R using binary search, and once we figure out this point R, we will simply add n minus R plus 1 to our result. And with that, the complexity is now reduced from order n square to order n log n. because we are only iterating over all possible else and not iterating over all the values of R. So let's just quickly reiterate over the entire final algorithm and do a dry run to conclude this. So what we will do, we will first figure out the max till the maximum value in the left, which is strictly increasing, so which we denote by m of L. So in this case m of L is this, so everything up till this is strictly increasing, right? Now in the same fashion this will be m of R. Basically everything up till this will be strictly increasing, so everything after this will be strictly increasing. Now to tackle, if you remember, to tackle the first criteria, we will not go, our L will not go from 0 to n, instead our L will go just from 0 to m of L, right? So we'll start our L from sorry for this, so let's say we'll start our L from here, right? Let's just, so we start our L from here. For this L, what we know that answer will be in this range, that we know, right? And we also know that there will be a point R after which everything will be valid, right? So we just need to figure out this point R and we'll simply add n minus R plus 1 to our result, right? So this point R, what will be this point R? The point R will be the one which satisfies this criteria. So in this case the value of L is 6. So for simplicity I am assuming that I am removing everything after L, right? So the value of L is 0, it means, okay, well, let's not do that. So value of L of 0, it means you are removing all the array starting from this index, right? Your removal subarray starts from this index. Now you need to figure out up till which index you need to remove. So you need to remove up till, or you must remove up till the index which is greater, up till you reach an index which is greater than the previous value. The previous value is minus infinity because there is no previous. So everything after this is actually valid because anything is greater than minus infinity, right? So your point R is this. Now think about this. This is valid array 1 2 7 8 9. If you remove this array, this is a valid array. Similarly, if you remove this one, this will form a valid strictly increasing array 2 7 8 9. Similarly, if you remove this one, again a valid array. If you remove this one, again a valid array. And finally if you remove this one, again a valid array. So how many valid arrays are there? N minus R plus 1. So these many valid arrays you will form, which is 6. So this is 1, this is 2, 3, 4, 5 and 6, right? So we figured out all possible valid array starting from this particular index L. Now comes this particular index L. So again we will do the same thing. We need to figure out the first R which is valid and after which everything else will be valid, right? So the first R which will be valid is the one which is greater than 6, right? So what is the first value which is greater than 6? 7. So everything after this will be valid. So how many arrays are there? Again 10 minus 7 plus 1, which is 4. So if you see, this is a valid array. So one array 6 7 8 9, right? This is a valid array 6 8 9. This is a valid array, and finally this is a valid array. So 4 arrays are there. Now final thing, if you give your L as this, it means you are starting your removal from here. So your R will be the one which lies after this value. So you have to figure out an index which lies after this value. You have to figure out an index which is greater than 7. So in this case this one. So number of subarray would be 3, right? And finally this is the last L which is possible. It means you are removing the subarray starting from here. So 6, 7, 8, you need something which is greater than 8. So only thing which is greater than 8 is 9. So you will have two arrays. One is this. Notice 6, 7, 8, 9 is a valid array. Second is this. Again 6, 7, 8 is a valid array. So two more array. So the final answer here is 6 plus 4, 10 plus 5, 15. So 15 incremovable arrays are there in this particular of this particular array. So hope this entire solution makes sense. The complexity is just order and log because we are iterating over L and doing a binary search to figure out the first R, and after that we are just doing a mathematical operation. So if you have watched this point, I would strongly encourage you to pause and try to code it by yourself and get it submitted as well, because until you see an AC, it means you are missing something. So try to get it submitted and see which part you didn't understand and come back and rewatch that section. So next we're looking at the code. Code is very straightforward. As we discussed, we'll simply figure out the max left and max right, this M of L and M of R. So I denoted that with LFT and RGT, and we figured out LFT and RGT in exactly the same way we discussed. After that we started our L from 0 to left. Notice one thing, in this explanation, the subarray starting from L will be removed, but in the implementation what I assume that everything after L is removed. So if L is this, it means we will remove the subarray starting from 8, right, and so on and so forth. So there is some difference between the indexes, but I hope you will understand this. The crux is same. So we'll figure out the first valid R, and once we figure out the first valid R, we'll simply add n minus R plus 1 to our result. Now there is just one edge case here. The edge case is if left is n minus 1, it means the entire array is already strictly increasing. Why this is an edge case, I would leave it to you. This might not be an edge case in your implementation, because there is a way to implement this without this edge case as well. So if you go via this path, there will not be any edge case. Basically, if you assume that you are removing everything after L, starting from L, I don't think there this edge case will be there. Otherwise, you have to tackle this as well. So hope you understand the entire solution. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.